call Euclidean algorithm. So we have two integers, n and m. Let's make sure they're both non-zero so that there's no n and m integers. Well, integers, not necessarily naturals. And okay, well, fine. Let's say m is the bigger one, and let's say neither of them are zero. So I could have taken them. Okay, what do we do? Vendro? The division algorithm. So we write n as m times q1 plus r1. Let's call m r0, and let's call n r-1, just to keep the notation. And the point is, r1 is strictly less than m. Now, by the way, how do we know that how do we know that there is a division like this? We didn't prove it. We just said, I mean, it's obvious. It's what you did in grade school. But how do we actually know how to do this?
So I think last time we showed that the set of like all three combinations of mn is equal to like set generated by vi.
Now it's a little bit more subtle because, well, it's not really more subtle. Just the coefficient in front of n is 1. But it's the same idea. It's exactly the same idea. Look at the set n minus mq as q ranges over the integers. N is fixed. This is a subset of the integers. So let's call this S. It's a subset of the integers. And it takes on both positive and negative values because q can be both positive and negative. So depending on the sign, you know, when you make q either large negative or large positive, whatever you need to, this has positive and negative values. Takes, in particular, positive values. If we let r be the least strictly positive value, not strictly positive, because it might be 0, least non-negative value, and the claim, the only thing that we have to prove is that r is strictly less than m. That's this part of the inequality. That's the only thing that we need. Because if r is an element here, then it's of the form n minus mq for some q. And it's non-negative, so we have our expression, except we want to make sure that it's strictly less than m. If not, so r is bigger than m, greater than or equal to, and look at this expression, n minus mq. So this was n minus mq equals r. Well, I can subtract m from this. Then n minus mq minus m is r minus m. But this is also m times q plus 1. So this is an element of S. And this element of S is also non-negative, because we assumed r is bigger than m. And that contradicts the fact that r was supposed to be the least non-negative element. Contradiction, since r is least such. Least non-negative element of S. That's how we defined r. So that's our contradiction, and that implies r is less than m, and ends that parenthesis. In a minute, we're going to generalize this, so that's why I'm kind of making a big deal out of something that seems trivial. That's the beauty of generalization. It makes you really understand, do you understand the thing that you thought was trivial? Okay? So, a slight subtlety in this division algorithm. So what we did is we did one step in the division algorithm. We got a number R1 that's strictly less than m. And then what did we do? We're back to the Euclidean algorithm. We have two integers n and m. N is m times somebody plus a remainder, which is strictly less than m. Then we continue. Yeah, exactly. So continue, and at each stage we make so there exists a q, let's say j rj, such that if we take rj minus 1 times qj plus rj, that will make rj minus 2. So we keep doing the division algorithm. The first instance was with j equals 1. That's up there. R negative 1 is equal to R0 Q1 plus R1. And then we continue making more and more of these. At each stage, Rj is strictly less than Rj minus 1 and non-negative. And the weird thing about positive integers is if you keep decreasing them, strictly decreasing them, that can't go on forever. So this is again descent. Even this simple argument is a descent argument. Okay? This stops at some finite capital J. In fact, there's a universal upper bound for how long it could possibly go on, given our initial n and m. Certainly can't take more than m, for example, yeah, m steps, because each time you're subtracting at least 1 and you started with a number of size m. So you can't subtract 1 more than m times and remain positive. What does it mean to stop? It stops when r big J is equal to 0. It stops when this ceases to be the case. You can't continue the division algorithm and get strictly smaller numbers if Rj is 0. So when Rj is 0, that's when it stops. And the claim, so the theorem of the Euclidean algorithm, theorem is that Rj minus 1, the number just before the number where it stopped, is exactly the other than Debendro? Karen, you heard him say it. Yeah, GCD of n. Why? Bless you. Other than Debendro. You guys remember we watched it go last time. I put a few exercises. I hope you saw the exercises in the homework for this Friday. So you're going to get some good practice with this. How many are totally lost? There's too many symbols on the page.
I had a question. Why is up there when r minus m is an s?
Yes.
Why is that a contradiction?
Excellent. So we started with this set S, which is all the values of n minus mq as q ranges over the integers. And that's like an entire arithmetic progression. Both n and m are positive in this scenario. We said r is the least non-negative value in S. Okay? If r is bigger than m for some ungodly reason, well, what was r? It was this value. Right? Because it's one of the values in S. So there's some q so that this is true. But then take that value of r and subtract m, you get a new element of S. Because it's still of the form n minus m times an integer.
Okay.
but that new value is non-negative. And it's an s. And it's strictly smaller than r. But we assumed r was the smallest. So that's the contradiction. It's a contradiction because r was the least such element of s that's non-negative. So that's why r has to be strictly less than l. These trivial things in the integers are what's so hard to prove, but I hope to convince you in just a few minutes that they're worth doing, because we're going to do it in a non-trivial setting in a minute, where all of these steps, you'll actually have to scratch your head and question, is this really true? What am I talking about? Why is this true here and maybe not somewhere else? Okay? So the theorem that we're trying to prove, this is the main theorem of the Euclidean algorithm, is that the number that you get when you stop, when you get this remainder 0 in the last step, the previous number is exactly the GCD. Okay? So we can prove this like analysts. Let's prove that it's at least the GCD and it's also at most the GCD, and therefore it's the GCD. Okay? So proof. Well, if some number L divides N and L divides M, then remember what we do at the very beginning of the Euclidean algorithm. We start with R1, which is N minus MQ1. This is a multiple of L, this is a multiple of L. The whole thing is also a multiple of L. Has L as a divisor. And then what do we do when we continue? At each stage, all of the r's have L as a divisor. If L divides Rj minus 2 and L divides Rj minus 1, then Rj, which is Rj minus 2 minus Rj minus 1 times Qj, I'm just rewriting this equation where I'm isolating Rj. We assume that L was a divisor of both of these things, so it's also a divisor of Rj. Has L dividing Rj. And so this last guy, when we stop, Rj minus 1 has L dividing Rj minus 1. That's true for any divisor of both L and M, so it's true for the GCD. The greatest common divisor of both N and M will also divide, which implies the GCD of N and M divides Rj minus 1. So that's one direction. Does that make sense? We're seeing why does this algorithm actually give us the GCD? Well, when it stops, it has to give us a number at least as large as the GCD. It gives us some multiple of the GCD. Now let's look at what happens when it stops. So that's one direction. The other direction is we want to prove that Rj minus 1 is itself a divisor of both, and hence it's a multiple. It is a divisor of the GCD. You'll see in a second. I mean, we saw the explicit example last time, so I'm hoping that the algebraic version of this is okay. Anybody lost? Be honest. Yukong, will you raise your hand, please? Is anybody lost? You have to raise your hand for it to work. Can you? I know you're not lost. Just raise your hand for me. Yeah, nice and high. Is anybody lost? Nice and high. Pretend you're lost. Do me a favor. No, high, high, high. High up in the air. Good. Anybody lost? See, now you ruined it. It only works if you play along the first time. It's an amazing piece of psychology I learned a long time ago. People are too afraid to raise their hand until they see someone else has raised their hand. Even if they just heard me ask them to raise their own hand, it works. But you got to do it the first time. Okay. Is anybody really lost? Will's good. Thank you. Thumbs up help. Thumbs up tell me you're with me. Good. Now let's go the other direction. Why is the other direction So need to show, or want to show, need to show that Rj minus 1 is also a divisor of both n and m, and hence of the GCD. But look at what happens at this last stage. When Rj is equal to 0, look at what happens. Rj minus 2, Rj minus 2, I'm just reading this equation, but with capital J, that place where we stopped. Rj minus 2 is equal to Rj minus 1 times Q, that's supposed to be a Q, J, plus Rj. But Rj is 0. Which means Rj minus 2, Rj minus 2 has Rj minus 1 as a divisor. And now we induct this back up. Now follow the induction and iterate this back up. Follow backwards. So both of these, all Rj have Rj minus 1 as a divisor. For the same reason, if you just write what the equation is, this guy and this guy have this Rj minus 1 as factors. So this one does, and then the next one does, and so on. And it works its way all the way back up for all j, including j equals 0, which means Rj minus 1 divides m, and j equals minus 1, which implies, if you remember, R0 was m, and R negative 1 is n. And if both n and m have Rj minus 1 as divisors, then so do their GCD. And if it divides the GCD and the GCD divides it, and they're both positive integers, then they're equal. Okay? Any questions in this proof? Tell me, Sean? Connor.
Yeah, just the last line and j equals negative 1. You said that part again.
Yes. That I should show all the way back up here. I just named R0 to be m and R minus 1 to be n. So this is true for all Rj, but including the case j equals 0, which is m, maybe I should say, which equals R0, and n, which is R negative 1. Okay? I'm stepping up our level of sophistication yet again, so if it's going too fast, I'm trying out a slightly faster speed. If it's going too fast, tell me. I want to see how much you guys can take. All right. Let's bring in some fancy words. Just so that you're exposed to them. I mean, we're not going to use them too seriously yet, necessarily. So you remember we talked about this. So given nm, given n and m, let's say not equal to 0, we looked at what we said was s, nx plus my, as x and y run over the integers. Right? This is a subset of the integers. S is n Does anybody know the word that I'm about to say? It's okay if not. It's an ideal. You've heard that before.
I thought it was just multiplication. But
Yes, what does it mean to be an ideal? So just to give you some sense.
Isn't it if one element's in the set, then any element multiplied by that element in the set is also in the set? Is that it?
That's one defining characteristic. If we have any element of S, then any integer multiple of that element is also in S. I need one other thing. Karen? Closed under addition. Addition and subtraction. Z1, Z2 in S, then Z1 plus and Z1 minus Z2 is in S. Let's leave that as an exercise. I think that's a good exercise. And this is a general thing that you do for any ring. Inside a ring, you can have ideals. So, exercise. Exercise. Prove this. Prove that S is an ideal. It's easy to see, right? If you have, well, let me not do it for you. It's easy to see. You're not going to have a hard time with this one. And if you have a hard time with this one, ask your neighbor, work with somebody, come to office hours. I'm happy to talk about it. Let me not give it away. The language of ideals is very useful in a lot of ways. Let's prove a theorem. Yes, Karen?
There are a lot of things that are like closed over addition and multiplication, right? So like what's the difference between an ideal and a field?
Okay. All right, so before we state this theorem, let's talk a little bit about names of these structures. So some names, fancy names. Fancy, but they're not just fancy to be fancy. They're fancy because they're important, and so many things fall into these categories. So there's a group. What does it mean to be a group? You have some operation. It's a set of things, set with operation. Let's call that operation plus, although a lot of times that operation will be denoted something else. Sometimes is the other most common thing. A zero, an identity element, and inverses. So let's have some examples of groups. What's a group? Is the natural numbers a group under addition?
No.
We have an operation. We can definitely add two natural numbers. We have a zero. So what does it mean to have a zero, by the way? Zero means for all x in your set, let's say S, x plus 0 equals x. Doesn't do anything. What do I mean by inverses? So that was what I mean by a zero. What do I mean by inverses? I mean for any element, there exists some other element, so that if you, whatever the operation is, if you add them together, you get the zero element. So this is why Stephanie is very adamantly saying the natural numbers do not form a group.
Do you need to have only one operation in your group, or can you have multiple?
You can have multiple, but the group itself, the group structure only assumes one. So I can multiply natural numbers and get natural numbers. I can add natural numbers. That's why I put n with a plus. Is that a group or not? So I have to specify which operation I'm speaking about if I have more than one floating around. I can also take an integer and exponentiate it to another integer. I mean, these are the main things you want to think about. I don't know how much we want to go into all the different, there's monoids and semi-groups and groups and semi-rings and so on. But these are the main examples. You should keep these examples in mind. So no, it fails this condition. Given a natural number, there does not exist another natural number such that when you add the two together you get 0. But the integers with addition do form a group. So the integers are a group under addition because there is a 0 that you added a 0 to any integer, you get that integer back. For any integer, there's the negative of that integer, so that when you add the two together, you get the identity element. Okay? And then let's skip right to a ring. A ring is another fancy term, technical term. You know, mathematicians abuse words that non-mathematicians know what a group is, like a bunch of things. No, group has a very technical meaning. What's a ring? What's a round thing you put on a finger? No. There's a reason. It's because it kind of closes up. Anyway, all of these words have long convoluted histories that everyone has forgotten and no longer uses. So again, it's a set, S, with an operation plus, under which it's a group under addition, and there's a times. And there are other axioms. Let me not give you the complete axiomatization. You need to be able to add, subtract, and multiply. That's what you need to be a ring. Okay? So the integers are a ring. Because you can add, subtract. I didn't say divide. Just add, subtract, and multiply. You can add, subtract, and multiply integers, and that's a ring. Yes. And the last one, this is an important one, is the notion of a field. So kind of the hierarchy is group, all you have is addition and subtraction. Ring, you have addition, subtraction, and multiplication, but not necessarily division. I can't divide two integers. And a field is, again, a set with an addition and a multiplication operation, but now I need to add, subtract, multiply, and divide. In other words, what do I mean by this last one? I.e., for every element of S, except the identity element of addition, whatever that may be, there exists an element y in S, so that when you multiply them together, x times y, you get the identity element of multiplication. Okay? That's what it means to be a field. And these things should be commutative, and they should be associative, and there are all kinds of other rules that I'm suppressing. But the key characteristics are exactly these. I wasn't going to go into this, but actually, since you asked, let's prove a theorem. Fine, let's do it. Theorem. Z mod nz. Those residue classes, Z mod n. What are the residue classes mod n? With usual addition, but of course addition mod n, and usual multiplication, of course, mod n. This is a field. What's that? Z mod 4 is going to have trouble being a field. Z mod 6 is going to have trouble being a field. It's a field if and only if n is prime. These are called the finite fields. So in Z, I can already add, subtract, and multiply. So in Z mod n, I can add, subtract, and multiply. The only question is, does every non-zero residue class have an inverse? What do you mean an inverse? What's a half in the integers? A half is not in the integers, right? So what is a half in Z mod 11? So Z mod NZ, or Z mod N for short. That's the question. We have to be able to understand what is a half. In other words, what's the inverse, multiplicative inverse of the number 2 in Z mod 11? Does anybody already know the answer? Okay, good. We're all about to learn something. So think about that. What should that mean? i.e., a number y such that 2 times y, what does it mean to be a half? A half is a number that when you multiply by 2, you get 1. So I want 2 times y to be 1 mod 11. How many people know such a number? Okay, so now almost everyone has such a number in their mind. Those that don't, take another minute. See if you can think of such a number. I want to be able to solve this equation. And if I can solve this equation for any x except 0, for any non-zero x, then I have a field. Will?
I just have a question. So I get the right equation, like we could solve that. But then how do you extrapolate that equation from what is 1/2?
Well, when we say 1/2, what do we mean? Well, we mean the real number, 1/2, right? Halfway between 0 and 1. No, what we actually mean is the number so that when you multiply by 2, you get 1.
Okay.
So we're literally solving this equation. In the integers, this equation has no solutions. The integers do not form a field. They form a ring. We can add, subtract, and multiply, but we cannot divide. There's not an integer so that twice that integer is 1. But when we look at modular arithmetic, especially for the prime moduli, we can always divide unless we're dividing by 0. So now does everybody have the number? You want to say it all together? 3, 2, 1? It's actually the product of 3 times 2 times 1. Yes, so y equals 6, because 2 times 6 is 1. It's 12, which is 1 mod 11. What's a third? Mod 11. Take a minute. How many know the answer? Give me a hand when you have the answer. Okay. Think about it. Has everybody got it? Of course, I should put, it's not a third as a real number. It's the number that when you multiply by 3, you get 1. You triple it and you get to 1, the multiplicative identity. Does everybody have it? Ready? On a count of 4. What's the answer? 4. Yeah? So 3 times 4 is 1. So 4 is equal to a third. I mean, again, not really, but the point is we can solve this equation. That's what it means to be a third. Okay? Inverse of 5. 5 inverse. What's a fifth? Mod 11. And then I'm going to ask for a 6th and a 7th and an 8th. So think about it. Actually, what's a 6th? 2. We already knew that. So a 6th is 2. Let's make a little table. Let's make a little table. So here is Z mod 11, except 0. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11 is 0. And x inverse. 1 over x. 1 over 1? That's easy. 1 over 2? 6. 1 over 3? 4. 1 over 4? 3, because 3 times 4 is 1. So a fourth is 3, a third is 4. A fifth. 9, you already got it. Why is that? 9 times 5 is 45, which is 1 more than 44, so 9 times 5 is 4. 9 times 5 is 1. So is 5 times 9. Okay, fill out the rest of the table. Take 2 minutes. Fill out the inverses. Is that a question, Connor, or just a stretch? Give me a thumbs up when you have the rest of the table done. Does that mean that a thumbs up or that's it?
Yeah, I got it.
Got it. Talk to each other, argue, cheat. Got it? Make sense? Cool? Weird? Okay, you want to tell me what a sixth is? Oh yeah, we knew that already. Sorry. Want to tell me what a seventh is? Right, 56 is 55 plus 1. So this is 8, this is 7, and -1 times -1 is 1. So that's always going to be its own inverse. Great. So everybody has an inverse. So Z mod 11 is a field. How about Z mod 12? Z mod 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay? X inverse. Inverse of 1, 1 times what is 1? 1 times 1 is 1. Okay. Inverse of 2. 2 times what is 1 more than a multiple of 12?
There's no inverse.
Why?
Because 12 is not prime. So 2 times, well, it can only become a factor, but it is an even number, so it can never be an odd number. It can never be 1 more than 12.
Right. We're trying to solve the equation 2 times y is congruent to 1 mod 12. In other words, i.e., 2 times y is equal to 1 plus a multiple of 12. Oh, thank you. Sorry. In other words, we're trying to solve the equation, I guess 12m, even though it's the negative of the m here, but it doesn't matter, it's the same integer, plus 2y is equal to 1 in the integers, which is exactly what the Euclidean algorithm is supposed to help us do. And you see plainly that these two are even. Can't get, so this has no solutions. 2 has no inverse, mod 12. How about 3?
Also no inverse.
Also no inverse. For the same reason, if I put a 3 here instead of a 2, both things here are multiples of 3. DePetro. Oh, everything that has a factor in common with 12 cannot have an inverse. So 6 can't have an inverse because this will be even. 8 can't have an inverse because that'll be even. 9 can't have an inverse because that'll be a multiple of 3. 10 can't have an inverse because that'll be even. So our only options are 1, 5, 7, and 11, and those are exactly the numbers that are co-prime to 12. So what's the inverse of 5? We don't have so many choices now. 11 is negative 1, so it's going to be its own inverse. And then all that's left is 5 times 7. 5 times 7 doesn't work. Devendro's desperately trying to get me to figure out that 25 is 1 more than 12. And 49 is 1 more than 48. 25 is 1 more than a multiple of 12. Okay? So 1 is its own inverse, 5 is its own inverse, 7 is its own inverse, and 11 is its own inverse, mod 12. And those are the only numbers that are invertible. So now you see this theorem is actually very easy, and it's exactly an immediate consequence of the Euclidean algorithm. Question? Right? How do you prove this theorem? Maybe let's make, this is a good place to make an exercise. Exercise. Table of x versus x inverse in Z mod 17. It's not going to be that hard. You only have 8 equations of this form to solve. You can guess and check, but you could also use the Euclidean algorithm. Okay. Exercise 2. So make exactly this kind of table. And now we can prove our theorem. Proof of theorem. So there's an if and only if. This ring Z mod NZ, where we can add and multiply and subtract, we can always add and subtract, we can always multiply, the question is can we divide, is a field if and only if n is prime. So there's 2 things to prove. If n is prime, then we can always divide, and if n is not prime, then there will always be numbers that have no inverses. So if n is prime, let's say p, why does every number have an inverse? Does a, which is not 0 mod p, have an inverse, a inverse? So some people write that a bar, a inverse. So it feels funny to write a half. So really what you write is 2 bar. Like a complex conjugate, but it's not a complex conjugate, it's a multiplicative inverse. Well, what equation are we trying to solve? So let's say if b is this hypothetical inverse, a inverse, what we really mean is that we want a times b is congruent to 1 mod p, i.e., what are we trying to solve? Devendra. Yep, ab minus a times b minus a multiple of p is equal to 1. But a and p are co-prime, because a is not a multiple, doesn't have p as a multiple. But a and p are co-prime, so this equation has solutions. So there exist b and m solving such that star holds. This is star. Okay? So you can always solve this equation, which means you can always solve this equation, which means Z mod PZ is always a field.
So since A doesn't equal 0 mod P, can you use Fermat's relative to find B?
Yes, in fact, that's another way of finding B inverse. Excellent point. Excellent point. So this is Devendro's method. If you want to do it this way, you could do exercise, so remark, use Fermat's little theorem for finding inverses. If A to the p minus 1 is congruent to 1, then a to the p minus 2 is the inverse. Times a is equal to 1. So this is a inverse. So that's one algorithm. This is something you can do efficiently. You can also just efficiently solve this equation. Do you guys know how to raise numbers to large powers efficiently? No. Modular powers. Good. So, okay, this is important. We got to know how to do this. Let's find the inverse of 5. Okay. Let's find. Here's an example. Let's do this efficiently. I'll give you one entry in your homework, which is what's the inverse of 5 mod 17. Find 5 inverse mod 17. Okay? That means we have to raise 5 to the 15th power. You try to put that in a calculator and reduce mod 17, you're going to be in big trouble. So here's what you do. So we want 5 to the 15th. That's a giant number. We reduce it step by step. First we look at 5 to the 1. Well, that's 5. So this is 5 to the n. Here's our little table. But it's not really 5 to the n, as you'll see in a second. So, and this is the mod 17. I should really call this something else. So 5 is 5. 5 squared is 8. 25 is 8 mod 17. 5 to the 4th is 8 squared, 64 mod 17. Oh, geez, 51 leaves 15.
So minus 5.
Minus 5? Is that right?
Or mod 5.
So I want 8 squared. 8 squared is 64. 64 mod 17. 51 is a multiple, is 17 times 3. So I'm left with 51 to 64 is 13. And 13 is minus 4, if you want to do it that way. Let's just leave it as 13, although for what I'm about to do next, it's better to use minus 4. Okay, so 5 to the 8th is 13. Oh, can't see. 13 squared. 13 squared is very big. Negative 4 squared is not so big. Negative 4 squared is 16. 16, which is also negative 1. And now I'm done, because 5 to the 15 is 5 to the 8. 15 in base 2 is 8 plus 4 plus 2 plus 1. So you write your exponent in binary, and then you very efficiently, by repeated squaring, can find this thing. So this is not hard to multiply all together. 5 times 8 is, so I just need to multiply all of them together. Let's see, what's easy to multiply together? 5 times 4 is easy. 5 times 4 times negative 1 is easy to multiply together. Negative 4 times negative 1 is 4. 4 times 5 is 20, which is 3. So I just need 3 times 8, 24. 7. And 5 times 7 is 1, because it's 35. Does everybody see that? Okay, so this is another method, another very useful method, because you don't do 5 times 5 times 5 times 5 times 5 15 times. You do iterated squaring, and then write your exponent in its binary expansion. So if we needed to raise this to the 13th power instead of the 15th, which exponents would we combine? 8, 2, and 1. 8, 4, and 1. 8, 4, and 1 adds up to 13. Okay? So you should be able to very quickly exponentiate in modular arithmetic. And that's why you can very quickly, using Fermat's little theorem, find inverses. You can also just directly solve the Euclidean, use the Euclidean algorithm. That's also very efficient. Okay, so you have two ways of efficiently finding inverses. Finding inverses is easy. Cool? Any questions? Okay, so the first part of the proof of the theorem is that if you have a prime, then every element is indeed invertible. The second part is of the theorem. The theorem says you have a field. Let's see, here's our theorem. You have a field if and only if n is prime. So if n isn't prime, what can't you invert?
Anything that's not
Anything that's not
co-prime.
coprime. Okay? So proof of theorem part 2. Proof of theorem continued. If n is not a prime, let a not equal to 0 mod n have a factor in common. Or just take a divisor of n. Have GCD of a and n bigger than 1. Then a times b plus nm equals 1 has no solutions. Precisely because this has a solution if and only if the GCD is equal to 1, because the Euclidean algorithm computes the GCD. So a times b is congruent to 1 mod n has no solution. So a does not have a multiplicative inverse, and z mod n is not a field. Some numbers will have inverses. In fact, exactly the ones with GCD equal to 1 are the ones that have inverses. So let's make a little definition. Definition, z mod nz cross is the set of a mod n which are invertible. These are called units also. Units. So these are numbers a, so there exists a b such that a times b is equal to 1. Okay? Let's do a little exercise. This is exercise 3. Compute z mod, give me a nice, not too composite, but a little bit composite number. 40? 4? Too easy, 40. And there's something called the Euler phi function, Euler totient function. Phi function, phi of n, which is the number of elements in z mod n cross. Phi of 40 is how many numbers are there in z mod 40 that are invertible? The cross means, z mod nz cross means the set of all things that are multiplicative, that have multiplicative inverses. In other words, how many numbers are co-prime to n by the previous discussion. Cool? What is z mod, what did we just work out a second ago? We had a table of the multiplicative inverses of 12. What's phi of 12? How many numbers are invertible mod 12? 1, 2, 3, 4. What is the group of units? Again, that just means what's the group of invertible elements? 1, 5, 7, 11. Those are the only invertible guys. What's the group structure of the group of units? So it's an abelian group of size 4. Have you guys seen structures of abelian groups? It's okay if not. There's a question here about is there an element of order 4 or not, but every element has order 2. 5 squared is 1, 7 squared is 1, 11 squared is 1, 1 squared is 1. So the group is Z mod 2 cross Z mod 2. Never mind. We'll come back to that. Okay, is exercise 3 clear? So you compute Z mod 40 cross this invertible group. In other words, who up to 40 is coprime to 40, and how many are there? Count them up. So far, so good? Pretty easy? Okay. So again, we're kind of stepping up our language game, getting fancier and fancier. So let's prove that Z is a principal ideal domain. Theorem. Z is a ring, is a PID. This is a principal ideal domain. What in the world can that possibly mean? An ideal, remember what an ideal is. It's a set S in your ring so that Z1 and Z2 are in S implies Z1 plus or minus Z2 are in S. So you can add and subtract. And Z and S are in the original, in the ambient ring, implies Z times R is in S. Okay, so every integer multiple of something in S is also itself in S. Okay, so what does it mean to be a principal ideal? So definition. Ideal S is principal. It's kind of another funny old word. What is principal? The principal of the school is like the one person that's responsible for the school or something. So there's an ideal is principal. Yes?
Is it can be generated by 1 unit?
Exactly. By one element.
Yeah.
That element doesn't have to be a unit. In fact, if it's generated by a unit, then it's the whole thing, right? We'll come back to that. But exactly what you said. So an ideal is principal if there exists an element, let's call it D, in the ring, but of course also in the ideal, such that S is the ideal generated by D. So now we have to unpack what that means. How do I generate an ideal by an element? We can do this in general, but we can also do this in particular in our ring Z.
If you multiply that element by different, either you raise it to a power or multiply it by other elements, and it can be every other element. And it has an answer for every equivalence class.
I like the first thing you said. All you do is, what are you allowed to do? You're allowed to add and subtract things that are there. So you give me D, and then I do all of these operations to D. So I take D and I take all multiples of D. That has to go in our set. And then we're automatically closed under addition and subtraction because multiples of D added and subtracted to one another are also still multiples of d, just by other integers. Okay, so this is just d times z. So the theorem is the ring Z is a principal ideal domain. The only ideals that we'll find are the ones that are generated by a single element. Weird? All right, so how do we prove this? Well, what's an ideal in general? You give me a bunch of elements, and I generate an ideal. So, in general, finitely generated ideals, so ideal looks like S, which is generated by a bunch of numbers, n1, n2, up to nk, let's say. So what is the ideal generated by a whole bunch of numbers? Devendra. Yes, exactly. Just as before, we can take any product of any of those numbers, but we can also take all sums and differences, but differences we have anyway because we have -1 as a multiple. So this is exactly the set of all linear combinations, n1 x1 plus nk xk, where the xj are all possible integers. So just as before, what we did with 2 elements, we can do with a whole bunch of elements. So here's an ideal. It's generated by a whole bunch of guys. How do I know that it's generated by, bless you, a single D? What is the D? So my claim to prove this theorem is that there exists some integer D so that S is not generated by k things, but just generated by one thing. Karen. D could be one. D could be one. But in general, it won't necessarily be one. Should I give you an example? 10, 14, 24. Take a minute and see if you can get a sense for what's going on here. So before we go on to the proof or even to the claim, so example, what is the ideal generated by 10, 14, 24? Go. Take 5 minutes. Talk to your neighbor. Start taking linear combinations of 10s, 14s, 24s. Add them up. Multiply them by your favorite integer. Add and subtract. What are you finding? What numbers are you seeing? And do they fit some kind of pattern? So cheat. Talk to your neighbor. Get some of these back. Andrew. Ariana. Michelle. Ray. Kevin. Will. Shane. Yukon. Sarah. Wenrui. And Charles. And somebody didn't put their name. So Please tell me. Because you're... Yes. Okay. You put your name on it and then you just back to it. I'll give it back to you. Give me a thumbs up when you figured out what 10, 14, 24 generate. Daniel, is that a thumbs up? Sheik, you got it? No? Okay, good. Good. It's challenging. Sheik, what numbers have you figured out so far? Who's in here? Well, 10's in there. 14's there. There are differences there. So 4 is in there. 14 is in there. I guess the 24 we don't even need because 24 is already in 10 plus 14.
Yeah.
So combinations of 24 can be made out of the 10 and the 14.
Yeah.
So
And the multiples, right?
So you just need 10 and 14 to represent what it is.
yeah. What else can we get? 20 and 28.
That represents 4.
And their difference will be 8.
8.
We can also get 0. Take the combination of none of them. True?
Is it just evens?
Will we get 2?
Well, we don't get 2,
We got 6 by
We
10
get
minus
30 and
12.
20 minus, say it again, 20 minus 14 is 6.
10 minus 4.
10 minus 4 is also 6. Yep, so we get 6.
30 minus
Connor?
28, we get 2.
30 minus 28 gets us 2.
28 minus 10 is 18.
28 minus 10 is 18. Yep. So Drew said all evens. Connor.
Since you have 2, doesn't that mean those could be all evens?
So since we have 2, we already know we can get all evens. Can we get any odds as linear combinations of 10 and 14? No. So we will get all evens. We will not get any odds. So this ideal is the ideal generated by 2. It is indeed principal. Does that make sense? By the way, what is 2? The GCD of 2 times 5 and 2 times 7. And 8 times 3. 2 times 2 times 2 times 3. The GCD of these 3 numbers is 2. Should I give you another one? Sure? Okay. Okay. It's not hard to prove this theorem, so I think we'll have time anyway. I don't know. 6, 18, let's do 22, and 5. So what's the ideal generated by these numbers?
Is it all integers?
Why?
There's a 1.
There's a 1. There's a 6 and a 5. So 6 minus 5 is 1. Once you have 1, you have everybody. So this is all integers, and all integers is the ideal generated by 1. It's also the ideal generated by negative 1. Ideals are nicer than numbers because they don't care about units. That's what ideals came from. The word there was like an ideal number when you. We'll get to that. We'll get to that. So what do you think D, what is D in this case? Well, it's 1, but why 1? The GCD. The GCD. These 6 and 5 already have no factors in common. Until I put the 5 there, it was looking even again. Okay, so D will be the GCD, greatest common divisor of all of these numbers. Let's try to prove the claim. So that'll prove our theorem. The theorem is that the ring of integers is a principal ideal domain. Any ideal is generated by a single element, and that element you can describe very easily. It's the greatest common divisor. So proof of claim: if L divides n1 and n2 and nk, then any combination of these has L as a multiple. Then for all z in S, L divides z. But that means the GCD of all the numbers divides every element of z. That implies the GCD of n1 through nk divides z for all z in S. So the only numbers we'll get in S are multiples of the GCD. Let's call the GCD D. So S is contained in dz. Now I want the opposite inclusion. Bless you. How do I get the opposite inclusion? Karen?
Suppose there's something in S that's not totally like
Yeah, it's even easier than that. It's even easier than that because I want to know that DZ, all of DZ is in S. So all I want to do is get D in S.
So we don't want to know that all of S is in DZ.
We know that all of S is contained in DZ. I want to know that all of DZ is contained in S. If I can get D to be contained in S, then all multiples of D are contained in S. And I have the inequality, I have the inclusion in the other direction. So for other direction, want D in S. How do I get D to be in S? Well, what does it mean for D to be in S, Daniel?
Well, you can pick like n1 and n2 and then go through the Euclidean algorithm process to find a linear combination to get to D.
N1 and N2 might have more factors in common than just D. N1 and N2, there might not be any two of them that have just D as their GCD. But maybe a third example, this is my favorite one, is 6, 10, 15. Any two of them have something in common. But using all three, right, you can get 15 minus 10 is 5. Once you can get 5 and you have 6, then you can get 1. And once you have 1, you have everything. But no pair of them gives you D alone, but you can run the Euclidean algorithm on all of them. Yeah, Debentra?
Can you pick an element in S and divide from the division algorithm by D?
Take an element in S and divide it by, and run the division algorithm with D.
And then once you have the remainder, show the remainder is an S, but the remainder is
Let me think. So you're saying take a
Like, I'm just trying to say that D is the smallest.
yes.
Yeah.
Yes.
Yeah. It's not
Okay.
negative.
So let R strictly positive be the least element of S.
And so that R has to be. If it's, yeah.
Yeah. Why?
Well, if you divide an x by r, you'll get a remainder. If you show that the remainder is in, then you can show that the remainder is in s. But that would also mean the r is, then the remainder is going to be less than r, which is a contradiction, so the remainder has to be 0.
Yes.
You-
Yeah, you can basically, I mean, it's the same argument. I mean, one thing you can do, I'm trying to bring it, there's a slick proof, but I don't want to be slick. Let's do what Daniel suggested, but in pieces. So first what we could do is we could take the ideal generated by pairs. There we have this Euclidean algorithm because we can divide one thing by another and do this division algorithm, and see that the ideal generated by these two things, so all linear combinations of these two things will be just some number, right? So the ideal generated by 6 and 10 is the ideal generated by 2, because the GCD of 6 and 10 is 2. And so any number here is just the linear combination of, any linear combination of 6 and 10 is just a multiple of 2, which means any combination of 6 and 10 and 15 is just a combination of 2 and 15. So you can do this in pairs. Knowing that it's true on pairs, you can build your way up to an arbitrary collection. So any linear combination of 2s and 15s will give you all the integers. Yeah, it's the ideal generated by 1. Okay? Does that make sense? So let's not do some fancy thing involving all of them. Looking in pairs, looking at n1 and 2, the ideal generated by just these two, gives you some d1 by exactly this argument, by the division argument, and then iterate and then add more elements. Add more elements to the full ideal, which will then be the full GCD. So it's D1 intersect D2 and so on, which is the full ideal generated by the full GCD. I ran out of time, so I rushed this last argument. Maybe I'll give you this argument again.